Another part of the responsibility of NASA is occupational surveillance for the astronauts, and that's really talking about their health and well-being as astronauts from the time they're brought into the Corps until they die. Because we expose them to certain unique environments, we still have responsibility to track their health and understand maybe how we've affected their health and life even after they leave the astronaut corps. So while in-mission is critical to completion of the mission in the agency, our directorate in particular considers their long-term health also our responsibility. So we use methodologies that are used in traditional occupational surveillance to look at the population, look at the workforce and say, what do we expose them to? How could it change the outcomes over time? What should we be looking for in the future? What could we measure? And how do we be smart about how we detect these things early and possibly can interfere and improve their quality of life? And so they have the lifespan that they were intended to have. We use a variety of different analogs to give us some insight to be able to smartly look for things. So if you're looking at things that impact from a remote deployment or confined space issues, we can look at the Antarctic, we can look at submariners. We also use a bed rest facility in a variety of locations where we keep people in bed at -6 degrees head down to replicate part of the microgravity effect on their physiology to say what happens to your body over time in this condition. Do a lot of testing before, during, and after the study to be able to measure things in people and then apply that to space to help us confine better what we're looking for, other than saying, well, we don't know what we don't know. We're not sure exactly how to go figure that out. So it helps us give some context to what it is we're looking for in the research that we fund. While all the analogs that we look at are important, they all certainly lack microgravity, which is predominant in spaceflight. And at this point, we tried to understand if any of the variables could be synergistic in that, like I said, we could replicate the fluid shift and some of the changes in a bed rest model, and we can replicate remoteness and the stresses of environment that remoteness bring, but we can't add microgravity on top of it until we actually get into space, and that's been kind of the unknown variable we've tried to track by doing research on the International Space Station. Radiation is definitely a concern for exploration missions. Not that it's not for ISS, but we have the protection of the Van Allen belts to help reduce the risk. We use a lot of terrestrial analogs and studies here on Earth to look at what happens when you subject bodies and cells to different types of radiation and how the cells behave, or what you could use to interfere with processes after radiation exposure has occurred to mitigate the outcomes. I think it's hard to say if it's the most severe risk we're facing. I think it has the most unknowns, and that sometimes makes it the scariest. But we're not exactly sure how to account for it at this point within the other physiology issues we're looking at.
Regarding monitoring and surveillance for potential decrements, there's some basic areas that we want to continue to look at. Before we set up our initial program with MIR and later with ISS, what we did a thorough study of other analogs for our future mission, which was ISS. And so we looked at Antarctic missions, we looked at Arctic missions, we looked at those stations, went up to the submarine pens in Groton and looked at the Navy, what the Navy had up there. And we actually went to these locales and talked to the people who dealt with personnel in those environments. And there was nothing exactly like the space station environment, just like there's not going to be anything exactly like a 2.5-year flight to Mars. But you can take elements, and we should continue to take elements from Antarctic winter overs, not just someone going to a summer station for 3 months, but as similar as possible to Antarctic winter overs, to very long submissions, to there have been other treks that have lasted a year or so. And we should look at the lessons learned from those and the practices, good and bad, and what's come out of those, and cobble together, as we did earlier, just cobble together a Frankenstein initial going-in program, best estimate. And of course, now we have the benefits of having ISS and having 6 and hopefully 12-month missions that we can learn from and put that into our Frankenstein and come up with a pretty good estimate of what we're going to need there. that's how we'll approach it initially.